Hello everyone, my name is Pierre Audisio. I'm a third year PhD student at the Lyon in the physics laboratory. And today I will present to you a restoration method based on plug-and-play approach that we have made with my director Nelly Bustenik and Barbara Belletti, both researchers at CNRS. So this study is a part of a bigger project called Lyon, standing for Global Urbanization, on which the objective is to study the impact of the urbanization on the natural dynamics of the natural dynamics of the river around the world. So the study area that we choose as a test site was the Lhasa River that we locate on the left image that you have here, pointed with the arrow. So we choose that river because it contains on a short section different hydromorphological characteristics, really interesting for our topic. That you can see on the right, it contains part of a braided section, also on a branching and straight area. Here, for example, in France, we are more familiar with straight and meandering area for a river. And in this case, the braided part is the much more complex that we can find. So it was a good training to see if our method works well. So in this study, we use two types of data, Sentinel-2 data and Landsat data. Landsat data, firstly, has the advantage of having a large historical coverage starting from the 17th. We have an example here of the image from Landsat. And secondly, we consider Sentinel-2 elements that have a higher resolution, but starting only from 2015. And so later, we have also created a database when both data were available. As I said, the main idea of that work was to create a restoration method for those type of hyperspectral images, to have a more high-resolution images on a long period, ideally from the 70s, and a more dense image available starting from the 15. So because it's a learned model-based method, we have firstly to define a model that is coherent with the data that we will use. So here we have the model that we use. We have ZB, with B the different spectral band that we considered. Z is the Landsat image at a lower resolution. We want to retract the higher resolution image that is contained inside Z, which is in our case Sentinel-2, as an example. So this image was degraded with a blurring kernel that we defined here as A. It was also downsampled with a scale factor equal to S. And finally, we also add noise to have a coherence between the Sentinel-2 data that we study and the observation that we had. The minimization problem associated to that model and to find an approximation of XAT, so the high resolution image from the observation, is the following. As you can see in the equation 1, we have a data fidelity term and a prior term. Usually that prior term is a non-differentiable function. That's why we need to use an iterative scheme to approximate our XAT. So the iteration scheme that we used was the forward-backward framework with a backward step associated with the prior, so our G function, and a forward step that could be associated with the data fidelity term. Depending on the function G that we choose, that backward step defined by d theta lambda tau could be, if we choose, for example, in the classical variational approach, we choose the total variation function, it will be the proximal operator of TB. But in our case, in the plug-and-play approach, that d theta lambda tau will be a learned denoiser. On that two approach, we have some specific theoretical convergence assumption. For the classical variational approach, we have to choose a specific value of lambda that you can see in equation 1, that the penalization term. And in the plug-and-play approach, we have again, with the specific choice of lambda, but also some specific constraint that we have to apply during the training of Ordinoiser. So to train Ordinoiser, we use 100, 200 image pair, which is not a lot. And in these different image, so Sentinel-2 and Landsat, we have four main spectral band: red, green, and blue, with the near infrared, which is really important for the detection of water. And so we extracted all those images based on the center line of the river. So we propped all along the river. And for the denoiser, we use here the architecture unit. And we train so on the image that you can see below with a reference image coming from Sentinel-2 and the noised version of that image just on the second line. So the training dataset here was just composed by Sentinel-2 image, one the original and one degraded. But later on slides that are coming, you will see that we have also different test dataset based on Sentinel and Landsat. So as I say, we have a real database, which correspond to Sentinel-2 and Landsat 8 pair of image. And secondly, we have a synthetic database that we use to calibrate our method to see if it works well and if it does not generate incoherent element during the reconstruction. So in the second database, the synthetic database, the synthetic Sentinel-2 image were obtained based on the Landsat degradation. And what I mean by that is that we take our high resolution image, we blur it, we downscale it, and we add noise during the elements that were present in Landsat to create that synthetic Sentinel-2 image. So also, as I say in the slide before, we have to choose a specific value of tau, the penalization term, to guarantee a convergence of our reconstruction. And we have different value on which the PSNR can converge. But as you can see on the left, we do not obtain a maximum value of the PSNR for each value of lambda and a specific value of the step size tau. Here we obtain, sorry. Well, I don't know how to do the line, but in the blue line, you see that we obtain a maximum. So in the blue line, you see that we obtain a maximum around the value of 20 for the PSNR and the step size of 3 with lambda, which represent the penalization term equal to 0.8. And you can see also the impact of the step size on the right image when we compare the evolution for different reconstruction methods in respect to the iteration. So you can see that for some step size, for example, here, the step size equal to 3 and 5, we have a convergence that remains stable along the iteration. But for other step size, for example, tau equal to 2, we obtain a maximum of PSNR, but after that, we have an important decreasing of the value. And that's not what we want. So considering now the reconstruction that we had obtained, as I said, we firstly try our plug-and-play method on the synthetic database that I designed it here by the S2/S2. And after that, we apply it on the real database that consists in the Sentinel-2 and L8, standing for Landsat 8 image. So based on the metrics that we choose, the PSNR and the SSEM, I forgot, but we compared also a plug-and-play method that you can see in the last column to state-of-art methods, so the classical bicubic interpolation, but also another learned-based model called Swinier, which use also a denoiser, and the denoiser was trained also on the same database that you saw before. So now, as you can see, if you take a look to the metrics, we can say that Swinier has the best metrics compared to the two other approach. A bit sad for us, But if we take a closer look to the image that we obtain on the reconstruction of the plug-and-play approach, we see that the river structure is more well reconstructed with our plug-and-play method. Typically, here with so the most important reconstruction, because it's directly on the Landsat observation, we can see that, for example, this part of the river is missing in our Swinier representation, and so it's an important element, and we also saw that fact in other reconstruction that we had obtained. And because we considered 4 spectral bands, so red, blue, and green, and near infrared, with near infrared, we were able to use some more geographical metrics. For example, the water area or the perimeter of the river that we designed here just below our image. And so to calculate this water area, we firstly have to calculate the spectral index called NDWE, so normalized difference water index, where you can see in a whiter tinter of gray the water area, and when it goes darker, it's more the rain. So starting from that spectral indices, we thresholded them to calculate the water area and compare it to the reference water area that we have with Sentinel-2 in the first column. Again, Swinier has the more approach value in square meter with our reference data, which is, again, really sad for us because the structure is, again, much more well conservated, and we have some much more details on the plug-and-play structure that we built. For example, here we have these 2 branches that appears here. We have a better conservation of the part. Some little elements are much more well preserved. So in conclusion of this study, we can say that we need some metrics that rely more on the geographical and structural river aspect than the classical PSNR and SSEM elements. And yeah, I think the plug-and-play method was also a good balance between a good reconstruction and maybe also it had some good value on the classical metrics, still under Swinier, but not bad. And if you want some more details, this work was accepted to ECAST this year, so there is the article online. That's all. Thank you.
Thank you very much, Pierre, for the nice presentation. We have time for 1 or 2 questions.
Thanks for the presentation. If you are so interested in the water structure and you show the evaluation and you say, okay, we focus on NDWE, why work in the image space and why not, for example, try to improve the resolution directly on the NDWE mask, or not the mask, but the NDWE synthetic channel?
Because if I understand well the question, the NDWE was calculated using the red band and the near infrared band. So we firstly need to recover a good reconstruction of those 2 bands jointly, and after that reconstruct the NDWE. But if your question was more why we don't start directly with the NDWE, I don't know, it's maybe too much focus just on the NDWE. And if we consider the 4 spectral bands that we use, we have also the possibility to calculate other spectral indices, like for example, the NDVE for a green area. So it opens much more possibility. If the reconstruction works well, it opens much more door. For sure, if we study direct reconstruction method on NDWE, we can try it to see if at the end we have some better image, but it will be really focused on that. Because we would like to see if the infrastructure around the river has a big impact. olsun.
Thank you very much, Pierre.